So today we are starting to see some examples of classical equations for which we can generate C0 semigroups. And we start with the heat equation. So the heat equation is given here in 3.1. And we look at a function of u of t and x such that the first derivative with respect to t is equal to the second derivative with respect to x. So we start by working on the interval 0, 1, which is in space dimension 1. And this has the advantage that we can do explicitly all the computations, and so it's good to have something concrete. And so the operator hey in this case is defined as in 3.2, and the domain is H10 intersected with H2, where these are the classical Sobolev spaces. So with that in mind, we are going to see if A generates a C0 semigroup. So in order to prove that our operator A generates a C0 semigroup, we are going to apply, we are going to study this operator, and our goal is to prove 1 and 2 here. So the fact that A is densely defined is actually, it's known from other courses, meaning that the H1 node intersected with H2 is dense in L2. This is a result that we assume known. And the fact that A is closed will follow from our concrete work on the resolvent operator here. So now we move to a step with concrete computations, and we are going to use the blackboard. So the key point here is to study minus A plus lambda identity. And so since we are interested in the norm of R, the resolvent operator, we're looking at this equation. Since we are in dimension 1, we can transform it into a order 1 differential equation, but with so it's not an initial value problem, but a problem with values given at the border. So now how can we solve this equation here? That's a classical question. So what we are going to do is we are going to define, for example, the matrix A, which is 0, 1, lambda 0. And now what we have to solve is U prime equals AU minus F with U equals UV and F equals 0 F. And so you should know that in this case, you can write u of x as, so the exponential of the matrix A times x times u at 0, or x equals 0, minus the integral between 0 and x of exponential ax minus y fy dy. Okay, so the point now is to compute as explicitly as we can this expression here. So the first thing to do is to compute this exponential, and to do that, the simplest way is to so compute the eigenvalues of A. So what is the what are the eigenvalues of A? So so A is 0, 1, and 0. And so you have first, so what is mu1? Let's say mu1 is the smallest and mu2 is the other one. What are the eigenvalues? So to compute the eigenvalues, we just so the trace of A is 0 and its determinant is minus lambda. So mu1 is given by a half of the trace, which is 0, plus the trace to the square minus 4 the determinant. So I got that. So this is square root of lambda. In the same way, so sorry, because I want this to be the smallest, so it's minus. And the other one will be, so I just replace the minus by the plus, and this gives square root of lambda. Okay. Now I would like, so let's recall that. So the exponential here of ax, if I write, so I have two distinct eigenvalues, so I can write A as P d P minus 1, where P is the matrix constructed with the two eigenvectors associated with the eigenvalue. So if I have that, I will have that exponential ax is P exponential dx P minus 1. And actually, so okay, and this is equal to P exponential minus square root of x 0, 0 exponential square root of, oh, so sorry, it's not square root of x, but square root of lambda times x. I will write it on 0 and P minus 1. So let us write it here. So exponential of ax is P exponential dx P minus 1, which is P exponential of square root of lambda times x minus so I want p and p minus 1 explicitly. And so to compute p is v1, v2, with the v1, v2 being the eigenvalues associated with lambda 1 and lambda 2. And so I let you compute v1 and v2. So let's do, that's the, so we got almost the results. So let's do it. So this is a very classical thing. So first, let's start with a v1. So we writing a minus lambda 1 identity is equal to, so lambda, so no, sorry, it's square root of lambda, right? Yeah, sorry, so lambda 1 is minus square root of lambda. Oh, so mu1, sorry, mu1, and mu2 is square root of lambda. So if I look at a minus mu1 square root of lambda identity, I got that. And so now I look at square root of lambda 1, lambda square root of lambda xy equals 0, 0. So it gives me y equals minus square root of lambda x. So we can take v1 equal to 1 minus square root of lambda. Okay, let's do the same for the other eigenvalue. It will give, in this case, minus square root of lambda 1, lambda minus square root of lambda xy, and this is equivalent to y equals square root of lambda x. So we can take phi2 to be 1 square root of lambda. So this gives me p equals 1 minus square root of lambda 1 square root of lambda. Now, what about p minus 1? So just so if my matrix is A, B, C, D, I know that its inverse will be A divided by AD minus BC times, so it will be here D and minus C, and here it will be A and minus B. Okay, so if I apply that to P, this gives me P minus 1 equals.
Excusez-moi, monsieur.
Yes.
Une question, s'il vous plaît. La méthode que vous venez d'écrire, c'est une méthode pour trouver l'inverse d'une matrice, c'est ça?
Yes, in 2 dimensions. Yes.
Pour des dimensions, c'est ça?
Yes.
pour 3 dimensions, il y a une méthode, c'est comme ça ou?
Yes, but for dimension 3 is not so useful because computations are more complicated. So, but for two-dimensional matrices, it's a quick way to obtain the inverse. Yes. It stands for this comes from the fact when you have a matrix A, you took A and it's called the matrix of the codeterminants. Let's say A bar, and yeah, so it will take me more than 5 minutes to explain that, but so it's easy to you call it the codeterminants, and putting the good coefficients here, you will get the determinant of A on the diagonal, and so if you divide by the determinant of A, you will get the result. But that's a known fact. Okay, so now if I apply that to my two-dimensional matrix, it gives me 1. So the determinant here will be 2 square root of lambda, and then I can finish. So square root of lambda 1 minus 1 and square root of lambda. All right. Okay, so what do we have? We have so lambda 1 equals minus square root of lambda. Lambda 2 equals square root of lambda. P equals 1 minus square root of lambda. 1 square root of lambda, and P minus 1 equals 1 divided by 2 square root of lambda, and all right, and so now I can write u of x equals P minus 1 plus integral between 0 and x of, so here P exponential minus square root of lambda x minus y 0 0 exponential square root of lambda x minus 1 P minus 1 and 0 f of y and dy. So now the point is to clarify that, and we will use the fact that, so u0 equals 0 and u at times 1, so this is at times 0. It's not time, it's the space, but okay. So let's try to have an explicit expression now for u of x with that. Okay, so with that, let's try to have an expression of u of x. So I will write u of x equals. So let's look first at p minus 1. And recall that we are considering u node equals 0. Okay. So if I look at p minus 1 times u0 v0, u0 equals 0. So I get only on the first component of p minus 1 times u0 v0 is nothing but minus 1 divided by 2 square raised in the square root of lambda v0. Okay. And after that, I will multiply that by this term. And since p, the first line of p is 1, 1. So at the end, I get exactly this term times this term minus 1. So it will be first so minus 1 divided by 2 square root of lambda exponential of minus square root of lambda x v node. Here I'm writing the first component of this expression, and plus so if I look at the second component here, we'll get 1 divided by 2 square root of lambda so the second component here of this vector is 1 divided by 2 square root of lambda. I have to multiply it by exponential and then 1. So finally I get plus 1 divided by 2 square root of lambda exponential square root of lambda x v node. And plus or minus, there's a minus here, so minus the integral. So I do the same. So again, I have 0 here. So it will be the same, but I have to consider instead of x, it will be x minus y. And instead of v node, it will be f of y with the integral. So minus integral between 0 of x of, so minus 1 divided by 2 square lambda exponential minus square root of lambda x minus y. And I have f of y dy minus integral between 0 and x of 1 divided by 2 square of square root of lambda exponential square root of lambda x minus y f of y dy. All right. So here I use the fact that v0 u0 equals 0. Now I can use the fact that u of 1 equals 0. Okay. So I have also that u of 1 equals 0. So this will give me 0 equals, I can put v node in front. And here it will be -1. This is 1 plus. Okay, I just replaced x by 1. I put v node in front, and minus. Okay, so this will be a plus because I have okay. And so I just write and here it will be then 1 minus. Well, hopefully I didn't do any mistake. So this gives me v node then. So finally v node writes as, so these fractions in front will cancel. So I get exponential. So exponential square root of lambda minus divided by that. So it's exponential square root of lambda minus. All right, so I have an explicit solution for u of x with that, and v0 v node is given by that. Okay. So what did we prove? We proved that for all such that minus a plus lambda I u equals f. All right, so we have defined the resultant operator. And so this means that R lambda A F equals U. Okay, so furthermore, we have, so if I look at minus U second plus lambda U equals F, if I multiply by U and I take the integral, I get minus U second U plus lambda integral U square equals F U. So it gives me lambda integral U square plus by integration by parts, and using the fact that I have the boundary conditions, gives me that. So finally, I get that lambda times the norm of U in L2 to the square is less than by applying Cauchy-Schwarz. It gives me the norm of L2 times the norm so it gives me the norm of F in L2 times the norm of U in L2. So finally, I get that dividing by the norm of U, it gives me lambda times the norm of U in L2 is less than the norm of F in L2. But that gives me that U is exactly lambda identity minus A minus 1F is less than 1 divided by lambda times norm of F in L2. So by definitions of the operator norm, this gives me that lambda identity minus I minus 1, the norm operator norm is less than 1 divided by lambda. So I have almost all the conditions for the Yoshida theorem that are verified. It remains to prove that, in fact, A is a closed operator. So let's do that. So first, so now lambda identity minus 1 is well defined in X equals L2. So it's closed because it's defined everywhere. Okay, and this implies that also lambda identity minus A is closed. So to prove that it's closed, let's sequence xn in the domain of the operator such that xn converges to x in L2 and such that lambda I minus 1 x n converges to y in L2. So I want to prove that, in fact, I can write y as lambda I minus A times x. All right. But this is okay because what? Because lambda I minus 1, lambda I minus a minus 1 is well defined and continuous everywhere. So I can just apply by applying lambda I minus 1. This gives me that xn converges to lambda I minus 1 minus a minus 1y. This is because lambda I minus a minus 1 is continuous. Okay? So, but I have xn that converge to x and xn that converge to this term. So these two terms are equal. So finally, I get that x equals lambda I minus a minus 1y, which gives me y equals lambda a minus a, lambda I minus a x. All right, and this gives so, therefore, lambda I minus a is a closed operator. And if lambda I minus a is a closed operator, so is a. Because I can just take the minus and add and subtract lambda identity, and that's good. Okay. And so we proved that. So this proves that A generates a C0 semigroup of contractions. So the last question is what to conclude with respect to equation 3.1. And to answer that, we have to recall some previous results from the chapter 1. So let's go back to chapter 1. Okay, all right. So here we are. So when, let's do that. So when A generates a C0 semigroup, then you see here in 3 that for each x in D of A, in fact, ST of x satisfies the differential equation S prime. So ST of x prime equals A ST of x. And so that's exactly, if you replace A by the second derivative, it gives the exactly, in this case, the heat equation. All right, if you replace A by the second derivative with respect to the space, this gives you the heat equation. So our solution of the heat equation is given by ST of x, where S of t is the semigroup, C0 semigroup generated by A. All right, so that's it. But so if you have to ensure that x belongs to the domain of the operator A. And yeah, so that was the purpose of today, to study in detail this problem. And so that's what we're done with that. So that's it for today. So for tomorrow, for next time, we will be interested in u tt equals uxx, and on so 0, 1 times 0 infinity plus u 0 t equals u1 t equals 0, and u 0 x is equal to let's say given function. And so this is the wave equation. And so again, we'll define an operator A, but we will first need to transform this equation to obtain ut equals a u, and then study again lambda identity minus a, etc. So that's the program for next week. So see you next week.